Now let's look at some calculations involving our equations for waves. The first calculation is, what is the wavelength of a microwave having a frequency of 3.44 times 10 to the 9th hertz? Okay, so we have, first of all, some given information. We have, what is the wavelength? So we're looking for wavelength. It has a frequency equal to 3.44 times 10 to the 9th hertz. And we also know that it is a microwave, which is a type of EM radiation. So we know that it's traveling at a speed of 3.00 times 10 to the 8th meters per second. So we know that from the previous slides, C equals wavelength times frequency. We're interested in solving for wavelength, so we're going to divide by frequency, and we can say that C over F equals wavelength. So we just plug in C, 3.00 times 10 to the 8th meters per second, divided by the frequency, which is 3.44 times 10 to the 9th. And remember that hertz equals 1 over seconds. I'm going to write it in that way because I think it shows the unit cancellation better. So that cancels seconds, and we're left with a value in meters, which is appropriate for a wavelength. So we have 3 times 10 to the 8th divided by 3.44 times 10 to the 9th. That gives us 0.0872 meters. Next, we have a helium neon laser emits light with a wavelength of 633 nanometers. So we have wavelength equal 633 nanometers. We want to know what is the frequency of this light. Since it is light, it will travel at this speed. Now, before we can notice that we have nanometers here and meters here, we need to do a conversion. There are 10 to the 9th nanometers in 1 meter. So that means that we're going to have 633 times 10 to the negative 9th meters, which is equal to 6.33 times 10 to the negative 7th meters when we move our decimal back for proper scientific notation. Okay, so now we have these values. We have C equals wavelength times frequency. We're trying to solve for frequency this time, so we're going to divide out wavelength, and we get C over wavelength equals frequency, because wavelength cancels on that side. So that gives us 3 times 10 to the 8th meters per second divided by a wavelength of 6.33 times 10 to the negative 7th meters. Plugging that into a calculator. And that gives 4.74 times 10 to the 14th 1 over seconds, which is equal to 4.74 times 10 to the 14th hertz. Next problem is we want to know the wavelength of X-rays having a frequency as given. So we have what is the wavelength? That's what we're looking for. We've got speed of light equals 3 times 10 to the 8th meters per second, and we've got a frequency equal to 4.80 times 10 to the 17th hertz. So if C equals wavelength times frequency, and we're solving for wavelength, we divide the frequency, and we get wavelength is equal to speed of light divided by the frequency of light. Speed of light is 3 times 10 to the 8th meters per second. Frequency is 4.80 times 10 to the 17th hertz. And that gives us 6.25 times 10 to the negative 10th. And remember, a hertz is 1 over second. So that cancels seconds and leaves us with meters. Final answer. Now let's take a look at all the various types of electromagnetic radiation. And we're going to look at this in the form of something known as the electromagnetic spectrum. The electromagnetic spectrum is really just an ordered list of the various types of electromagnetic radiation. This starts with, it says broadcast band, but then we look at radio, radar, microwave, infrared, ultraviolet, X-ray, gamma ray, and then we also have this section through here that we're just calling visible light, stuck in between a fairly narrow range between infrared and ultraviolet. And then we also have cosmic rays out here as well. So the electromagnetic spectrum is an arrangement of all forms of electromagnetic radiation in order of wavelength and or frequency. These are put in order of wavelength to begin with, and same thing down here. We're looking at red is the 700 nanometer end to 400 nanometers. But as we're looking at this, we can see that from the standpoint of wavelength, we have very long wavelength on this end in the range of kilometers, and over here we have very short wavelength. Now we have already said that where we have long wavelength, we also have low frequency. And where we have short wavelength, we have high frequency. The next question would be, is there an energy order? Well, as you look at this, if you have been around a little bit, you know that, for instance, X-rays. Most people have X-rays at some time during their life, but if you think about it, when you get an X-ray, generally speaking, you're probably going to be put in a scenario, and the person giving you the X-ray gets behind a shield and then presses the X-ray button. You may also have some body parts covered with lead plates and so forth to protect from the X-rays. You have a limited number of X-rays that you should receive within a time period. So X-rays are very high energy. Ultraviolet light. We worry about ultraviolet light causing skin cancers and damage to DNA and so forth. Gamma rays are extremely hazardous. This is what you would worry about following some sort of nuclear accident or a nuclear weapon going off or something, would be the gamma rays, which are very penetrating. So we find that the high energy end of the radiation spectrum would be out here with the high frequency end, which matches what we've said. Radio and microwave, for instance, you're exposed to that continuously. If you can get a cell phone signal, then you're being exposed to microwaves. If you can get a radio signal in your car, then you're being exposed to radio. So this is going to be the low energy band or low energy region. We're not typically concerned with these. Same thing with visible light. So really from here back would be the low energy end, and this low energy corresponds to low frequency. So there is an energy order. Okay? Within the visible ranges, visible range typically stretches from 700 nanometers to 400 nanometers, with 400 being the high energy end, things like violet, and 700 being the low energy end, or red. You should know the order of the visible spectrum, and that would be, of course, red, orange, yellow, green, indigo, I forgot blue, excuse me. Blue, violet is out here, and somewhere in this region is a small region known as indigo, I. So you end up with this acronym that most of you've probably seen, Roy G. Biv. Red, orange, yellow, green, blue, indigo, and violet. Usually in more current times, indigo is sort of blended into blue and violet, so there's a very small separation between those. This being the low energy end, this being the higher energy end, this being the high frequency, low wavelength, and this end being the opposite of that, low frequency, high wavelength, higher at least, and low energy. All right. Now, there are various types of spectra that we can look at that have meaning in terms of what we need to get back to, which is the structure of the atom. First of all is what we would call a continuous spectrum. That's really what you're seeing back here. You're seeing all the colors. It's unbroken. It's actually a better image than the one I have on the next page. But this is an unbroken Roy G. Biv. On the other hand, we also have sometimes, if we take a gas and we heat it up to the point that it's glowing, such as a fluorescent light bulb is a good example of this, and then we pass the light through a prism or something that's going to separate the colors out, what we find is that a certain gas, if it's, for instance, hydrogen, this is the color of hydrogen gas when it's glowing, only gives out certain colors when we come over to the spectrum. This is known as an emission spectrum, and it's also sometimes called a bright line spectrum. Then we have the opposite of that, where we have a light bulb that's going to emit basically a continuous spectrum. It then passes through a sample of a cold gas. The light then passes through a prism, and what comes out over here is lots of light, but there are certain dark lines that show up, and we call this a dark line spectrum. Also called an absorption spectrum and emission spectrum, respectively. The continuous spectrum, that's just going to come from a light bulb passing light through a prism, and then your eye is over here or something to visualize the light that's coming through, and you get unbroken. But if this is a gas, such as hydrogen, when it glows, it doesn't give off an unbroken continuous spectrum. It gives off certain bands of light. The absorption spectrum comes from, well, apparently comes from absorption. This gas is going to be absorbing from the continuous spectrum, from all the colors of light here. It's absorbing certain things, and those things are taken out when we look over here. This is the same gas. Okay, so these two gases are the same. And it's important to note as we look at this, when we look at what the gas is emitting when it's glowing versus what it's absorbing when it's cold, they match up nicely. Okay, so absorption spectrums and emission spectrums for an individual an individual gas of, for instance, let's say hydrogen, if this is hydrogen, it's going to have a relationship between the emission spectrum and the absorption spectrum, which is of importance to atomic structure. And then last of all, we talked about light being a wave, and it has all the characteristics of waves. It can be reflected, it can be diffracted, it can be refracted, but an individual in the late 1800s, very late 1800s, by the name of Max Planck, found that he could explain certain things about matter if he imagined that light was particulate. The idea of light being a particle actually originated with Isaac Newton, but it was never taken very seriously. This gentleman, Max Planck, a German, found that energy exists in discrete quantities, and he called those quantities quanta, or quantum. Quanta is plural. Sort of beyond this course to get into the description of why he came up with this idea, but for us it's mainly just important that he did. So light has particle, remember, means matter properties, not just wave properties. Remember, wave equals energy. This was confirmed by Albert Einstein in something known as the photoelectric effect. Photoelectric effect is the effect that you get when you have, for instance, a solar calculator and the light is bright enough in the room, you get electricity from it. Or when you walk in front of a door at a grocery store and it opens, that's a switch that's based upon the photoelectric effect and changes in the patterns of light. Street lights that come on at night work with sensors based upon the photoelectric effect also. So this was an idea proposed and then later confirmed by Einstein. And the other issue with Max Planck is he's the person that gave us the relationship. The amplitude of light versus the frequency of light is a measure of energy. The relationship there, this was the mechanical wave. Oops. But this was the electromagnetic wave, EM wave. So Planck is actually the person that showed us the EM wave is dependent, the energy of an electromagnetic wave is dependent upon frequency of light, not amplitude. Okay, and we get this equation. This is the Planck equation, E equals hf. This says the energy of a quantum is proportional to the frequency, and then we have this constant known as Planck's constant, which is 6.626 times 10 to the negative 34th joule seconds. And I would jot that down somewhere because you may need it for a calculation at some point. So this just says that energy is proportional to frequency and gave us a constant of proportionality to make it into an equation.